Welcome to the AI Research Roundup. I'm Alex. Today we're looking at a paper trending on X, published on February 3, 2026, just about 6 days ago. It demonstrates that weight updates in reinforcement learning are surprisingly sparse, allowing the authors to reduce the bandwidth required for training large models by over 100 times, dropping from 20 gigabits per second to just 0.2 gigabits per second. The paper is titled, Understanding and Exploiting Weight Update Sparsity for Communication-Efficient Distributed RL. And as we'll see later, the implications for running decentralized training on standard internet connections are really significant. So, Figure 1 illustrates the core problem and the proposed solution's impact. The vertical axis tracks compute utilization, meaning how efficiently the GPUs are being used, while the horizontal axis shows network bandwidth. The gray curve represents full weight synchronization, where you need a massive 20 gigabits per second just to reach 90% utilization. In contrast, the green curve shows the pulse method, which achieves that same 90% efficiency with only 0.2 gigabits per second. This 100 times reduction happens because pulse transmits only 140 megabytes of changed parameters, rather than the full 14 gigabytes. Well, Figure 2 validates the core premise by quantifying exactly how sparse these updates are. The left panel compares different model architectures, including Qwen 2.5, Llama 3.2, and Gemma 3. You can see that across every scale, from 500 million to 7 billion parameters, about 99% of the weights remain identical between steps. Moving to the right panel, the graph tracks what happens when updates accumulate over a gap of several steps, labeled as K. Crucially, even with the delay of 8 steps, sparsity stays above 98%. Alright. Figure 3 explains the mechanism behind this sparsity, which boils down to BF16 precision limits. The diagonal black line represents the minimum change required to update a weight. Mathematically, anything below it gets rounded to 0. The horizontal red line marks the maximum update size the optimizer can produce. As you can see, the cloud of gray dots, representing the model's weights, mostly falls in the pink region. Here, the weights are too large for the tiny updates to affect them, so they remain effectively frozen. So, while the previous figure explained the mechanism, Figure 6 shows the practical payoff during live training. The charts display two different tasks, math reasoning on the left, and code generation on the right. In both cases, the rising colored lines show that performance improves normally, meaning the sparse updates do not hurt learning. Crucially, the gray lines tracking data transfer stay flat near the dashed line at 108 megabytes. This proves that the method consistently delivers a 100 times reduction in bandwidth compared to sending the full 14 gigabyte model. Okay, confirming the mechanism from Figure 3, Table 2 lists the weight statistics for models like Qwen, Llama, and Gemma. The text explains that there is a critical threshold, about 7 times 10 to the negative 4, below which updates are lost in BF16 precision. However, the table shows the median weight magnitude is around 0.012, which is substantially larger than that limit. This discrepancy means that, as shown in the far right column, over 96% of the weights are too large to be modified by a typical update step. Well, having established that weights are generally large, Table 1 now examines the other side of the equation, the update sizes controlled by the optimizer. It lists the AtomW hyperparameters used by major frameworks and models like Llama, DeepSeek, and Qwen. Notice that while the PyTorch default for Beta 2 is 0.999, modern large language models typically use 0.95. This shift results in a much tighter asymptotic bound on the update magnitude, shown in the middle column. By constraining updates to about 1.4 times the learning rate, these settings ensure the updates remain small relative to the weights, reinforcing the sparsity effect. Alright, since the optimizer settings force updates to be small, Table 8 demonstrates how this translates into massive compression gains across different architectures. It lists performance metrics for model families like Qwen 2.5, Llama 3.2, and Gemma 3. The second column reveals that sparsity is consistently robust, staying above 99% in every case. Consequently, the full compression ratios in the fourth column range from 76 times to 100 times. Llama 3.2 is particularly notable as its slightly higher sparsity enables a full 100-fold reduction in data transfer. Wrapping up, two takeaways stand out. First, the interaction between BF16 precision and standard optimizers naturally freezes 99% of model weights during reinforcement learning. Second, exploiting this sparsity allows for a 100-fold reduction in bandwidth, enabling decentralized training on commodity networks without losing accuracy. That's it for this episode of the AI Research Roundup. I'm Alex. Thanks for listening.